It's my pleasure to host for the Brain Space Initiative, along with Armin Araji, Yingguo today. She is a professor in the departments of biostats and bioinformatics at Emory University. And she also leads the Center for Biomedical Imaging Statistics, CBIS, at Emory as well. And she focuses on analytic methods for neuroimaging, and she applies it to mental health and focuses on a lot of different things. And I think we'll hear about some of that today. And you're going to be talking about source separation framework for looking for hidden sources of the brain functional connectome. So we'll let you go ahead and share your screen. Are you able to do that?
Oh, yes, yes. Thanks to Armin.
There we go. Perfect. All right, great. So we'll let you take it away.
All right, okay. Does my screen look all right now?
Looks perfect, yes.
Okay, thank you. Well, first of all, I'd like to thank Vince and also Armin for inviting me to talk at the BSI Virtual Talk Series. It's really my great pleasure to be here and share some of our group's recent research. Particularly, because this research is about brain source separation for brain connectome, and Vince and your group are definitely a leading group in this area. So I would love to hear your feedbacks and suggestions for this work. Okay, so let me get started. And first of all, this is a joint work with my PhD student Jialu Ran and Yikai Wang, and also my current postdoc Yaotian Wang. Okay. Let me see. So basically, brain connectomics has attracted a lot of attention in neuroscience research and involved in all different kinds of neuroscience research studies. And we all know that neuroimaging techniques, especially MRI, has been playing a central role in study brain connectomics. Okay, so here there are different kinds of connectomics and functional versus structural. So in today's talk, I'll be focusing on analyzing functional connectomes, although the tools we have developed can also be applied to structural connectome as well. And so here is a typical pipeline. I know the audience here must be already very familiar with it, so I'll be very quick introduction. So we typically start with a specific brain atlas and extract it and node specific, activity time series, and then from study the dependent structure between those activity time series, then we can construct this kind of a functional connectome or connectivity matrices. And usually we would construct undirected connectivity matrices, which means they are symmetric from each other. And there are static FC functional connectivity versus dynamic ones. The static one has been investigated a lot in earlier days, and basically we assume stationary in the connectome structure across time and use the whole time series to generate the connectivity matrix. But people have found out actually the brain connectome reconfigures over time. So therefore dynamic FC has become more and more of a focus. Essentially, we use various methods. You can use different methods to basically estimate a series of connectivity matrix across time, which can help to reflect how the brain connectome, refigures and reorganizes. There are various ways to construct dynamic connectivity matrices. Here I listed just a few, some of them from the literature. A lot of those methods, basically what they produce, as I mentioned, is this series of connectivity matrices, which reflects the changes in the connectome. And one of the common goals in DFC is to try to identify whole brain or whole network DFC states. Some of the commonly used approach is to using some kind of grouping mechanism like clustering on those dynamic FC matrices to identify those latent whole brain DFC states. Okay, when we're looking at a brain connectome, we realize it's actually a very highly intricate system that actually involves a lot of underlying neural circuits. And correspondingly, our mathematical representation of the brain connectome, which are our brain connectivity matrix, represented the combined signal from many underlying latent connectivity sources, which we call connectivity traits. So each of the connectivity traits represent a collection of brain a collection of brain connections that tend to occur together during neural processing. And when we're thinking about these connectivity traits, they are kind of like reflect, each one of them will reflect a potentially underlying neural circuits in our connectome. And when we consider the reconfiguration of our dynamic connectivity system, what they actually come from is from changes in the up and down temporal expression of various connectivity traits. So from the temporal expression reconfiguration of those underlying traits, that resulted in the changes in the overall reconfiguration of the connectome. Okay. So it's very important to derive a reliable understanding of those latent connectivity neural circuits, basically to understand the brain organization. For example, in neurodevelopment study, they have found that for different neural circuits, they actually develops at different age, across time. During the neurodevelopment, and also when brain ages, different neural circuits also deteriorate at different rates. And those neural circuits also has important roles to play in mental health studies. For example, in psychiatry studies, through years of investigation, people have found specific mental disorders like PTSD, depression. They're generally characterized by the disruption in certain groups of neural circuits. So when you're looking at how those disorders affect the brain connectome, they don't affect all the connectome at the same time, but rather they disrupt certain neural circuits more dramatically. So therefore, understanding those underlying neural circuits can yield some new insights about brain organizations, and also to derive some new insights in terms of how different kind of brain diseases arises. However, it's not easy to study those underlying neural circuits for our brain. First of all, is that when we're looking at our brain connectivity matrices, they're usually high dimensional. For those very popular whole brain atlases that we use now, typically they will involve 300 or even more nodes in the atlases. So, and then since we are studying the connection between them, this will leading to, at least 40,000 to 60,000 connections based on a pairwise comparisons. Given this large number of connections, it's very natural there's a high possibility of spurious findings in our research in terms of, outcome-related brain connection investigations. And also, as we have mentioned, the observed connective matrix basically it reflects a lot of underlying inputs or underlying sources. And however, consistent dissection of the observed connective matrices is not very reliably established yet. So because of that challenge, it's often not very clear which neural circuits are the primary drivers of subpopulation differences or primary drivers of certain specific clinical symptoms. So that is actually what motivated us to proceed into this current research. And in terms of recovering underlying sources, we know that blind source separation framework has been very successfully implemented in neuroimaging community. They have becoming very robust method for decomposing neural activity signals, such as fMRI Bolt series, to review underlying brain networks. However, our focus here is brain connectivity matrices, which are kind of symmetric, matrices. So they have different properties as comparing to the neural activity signals. So that is why we need something specifically designed for them. And in the literature, there have been methods that has been proposed to decompose connectivity outcomes, like using dictionary learning or using PCA type of method. And the more advanced and recent framework in the literature now is like, for example, this method called CON-ICA, which essentially applies an ICA algorithm to decompose vectorized static FC matrices. And by using ICA, and they can retrieve some latent FC traits and review also some subjects loadings on those traits. So this method, I think, it's yield some very interesting new findings about the latent connectivity traits. However, there are still several major challenges that need to be addressed in such kind of analysis. Like in most of the existing methods, all the edges in the brain connectome are treated like independent variables or independent parameters. So we need to actually take into account of the dependence, actually topological structures across edges. Very fundamentally, when you consider the connection involving the same node because they derive from the same neural activity from that node, those connections are interconnected by nature. But this needs to be taken into account in the decomposition. And secondly, very importantly, because again, large number of connections in the whole brain connectome, we need some kind of proper sparsity regularization when we extract those latent sources, because otherwise the results may be too busy, and such that when you have such kind of busy estimates, it's hard to know where to focus exactly in each of the trait, and it also increase the risk of spurious findings. Additionally, when you have an noisy estimate, it can reduce the statistical power in your association analysis. I'm going to talk about some of that later. So what we are hoping to develop here are some robust source separation and decomposition tools for brain connectome matrices so that we can achieve reliable and consistent dissection of those matrices. The framework that we have been working on in the last several years is called LOCUS, which is a regularized BSS framework for brain connectome. And it represents, basically, the full name is a low-rank decomposition of brain connectivity with uniform sparsity. And we have a couple of manuscripts on this new method, a new framework, involving one paper about static FC and one paper about dynamic FC. Okay, so here is a summary of kind of like what is the contribution, mathematical or methodological contribution for this locus framework. First of all, it's designed for to decompose weighted connectivity matrices to review underlying traits. It's a general method that can be used to decompose static FC and also dynamic FC derived from various methods. So you can get the input from different, connectivity methodologies, and then the locus essentially take care of the next step. You took those connecting matrix, and then we will do source separation for them. Okay, so the key idea, one of the key methodology feature here is that when we extract those underlying latent connectivity traits, we use the low rank factorization so that we can efficiently capture those connectivity patterns and also account for the dependence between brain connections. This motivation actually comes from the neurological patterns of brain connectivity traits. So here I've shown some of the extracted functional connectivity traits from real fMRI data. So what we can observe is that a lot of them have this kind of a very special pattern, like a block diagonal pattern or banded structure, for example. So this type of patterns in matrices based on applied mass tensor method, they can be very efficiently captured using low rank tensor factorization. So that is what motivates us to develop this method. Additionally, another contribution of the method is we included some regularizations to improve the reliability in our source separation. So it includes two types of regularizations. We have the sparseness regularization for the spatial source map, which is this one's. And also when we are analyzing dynamic functional connectivity, we also include a temporal smoothness regularization so that we can improve the estimate in the temporal domain to recover the dynamic expression profile of those DFCs. Okay. So here next, please bear with me. I'm gonna introduce some of the underlying models for locus. So here are some notation introduction. When I introduce a model, I'm focusing on introducing it for dynamic FC because that is the more complex one. But basically the model can be reduced to analyze static FC automatically. So when we are analyzing DFC, I will denote YIT here to be like this symmetric DFC matrix for the I subjects measured at the T's time window or time period. And before we, so this is the dynamic FC matrix from a subject at specific time. And first we will use this mapping function, which I denote by this L. So this mapping function essentially take this symmetric matrix and extract the upper triangular elements of this connecting matrix to make it into this vector. And then once we did this transformation mapping, we're going to take these vectors and stack them across time and then across subjects. Then we can have this multi-subject DFC group matrices. So here is the decomposition model. We will decompose the observed dynamic data matrices of each subject at each time point, and to recover some population level latent connectivity traits. So the SL here represents the spatial source signal of the L's connectivity sources or trait, okay? And then basically those latent connectivity traits are combined via this mixing subjects and time-specific mixing coefficients and to generate the observed dynamic connectivity matrix for each subject across time. So these mixing coefficients for each subject, they will have a time series of this mixing coefficient, which we call trait loadings. And those trait loadings represent the dynamic temporal expression profile of this particular trait in these subjects. So if we look at, let me show you this one. So if we're looking at this graphic illustration, here, this is our original time series of dynamic FC matrices. And then through locus decomposition, we will extract, a total number of Q latent connectivity traits. And then each one of them will be associated with, will be mixed using these subjects, temporal loading time series. Basically, this loading time series is going to tell us when this trait is, highly expressed at a specific time for subject, and when this trait is kind of goes offline and doesn't appear much for that subject. Okay, so and then for each of the latent connectivity trait, we're gonna model that instead of treating it as a V by V matrix with all those independent parameters in it, we are gonna model it using this model, the tensor factorization, low rank tensor factorization, okay? So what this tensor factorization means is that we're going to decompose this connectivity matrix into those tensor product between those tensor vectors, which we call fibers in tensor literature. So, and then those fibers, X vectors, is actually what we call latent coordinates. So those latent factors represents the latent coordinates of those V nodes into a latent space. So what does this mean? The RL here is basically what is the dimension of that latent space. Okay, so what does this mean essentially? Here I have another figure to explain this. When we take a look at the original connectivity matrix, basically, is a V by V matrix, and then latent for the L's latent source, when we consider each node, that node in this connectivity matrix is characterized by its connection with all the other nodes in the system, okay? So which is a V by 1 vector. So this is very high dimension, as we can imagine, but that is how each of the node is characterized in the original connectivity matrices. And when we do so, also you may notice each connections in this matrix, original matrix, is treated as independent elements. So we are ignoring the dependence across those edges. For example, when we consider all the edges connecting to the same node V here, they're interconnected because they depend on the same node's activity. However, that dependent structure is not taken into account in the original connectivity trait matrix. And the number parameter in the original trait basically is in the second order of the number of nodes, basically. And what we are proposing is to actually model those connectivity traits using this low rank factorization. So what does this do is to project each node into onto a low dimensional latent space where RL here represent the dimension of the L's connectivity trait in this low latent space. And the XLV basically is the latent coordinate of a specific node in that latent space. So, and then when we consider the connection then between a pair of nodes, they are actually resulted from the inner product between the latent coordinates of the two nodes. So essentially that means when the two nodes have, similar, so that means this projection, this connection actually depends on the angle between these two nodes' latent coordinates. Therefore, those latent coordinates, you can imagine that actually they kind of reflect the neural activity underlying this trait of this node. So for two nodes that share similar neural activity, they'll have a smaller angles, hence they have a stronger connections. So this kind of actually coincides with the definition of brain connectivity in neuroscience. Highly connected nodes are the nodes that share similar neural activities. And also by using this low rank factorization structure, we can see the dependence between the connections involving the same node are taken into account because they will be involving they all involve the latent coordinate from the same node. Okay, so this is basically the some idea about the low rank factorization. And also we notice when we do this low rank factorization, then each node is characterized by its latent coordinates. Then we don't need to have this, second order number of nodes or parameter. Now the number of parameters now is in a linear order in terms of the number of nodes. So that could help us to reduce the parameters in our estimation. Okay, so this is basically like the gist of the dynamic locus model. And the trait loadings, as we have mentioned, will also be very useful because it can review how the different traits, becomes active and deactive across time. And it also allow us to study the synchronization between different connectivity traits. Okay. So this is here I have shown an example of connectivity trace. One of the connectivity traces extracted from real data and its corresponding latent space representation. So this trait is characterized by some connections involving the sensory and the somatomotor network, and also like the auditory network. So this is what this connectivity trait is mostly characterized by. And when we're looking at its corresponding latent states representation, and so here we project each of the node in this, this is the power atlas basically, by the way. So we project each node onto this latent space with dimension of 3. And we can see, and we color coded those nodes based on the functional modules of the nodes belong to. So one thing we find is that the nodes belonging to the same functional module tends to be clustered together in the latent space representation, which basically reflects those latent coordinates basically kind of as a reflection of the neural activity of those nodes. So that is why they're clustered together, because they are from the same functional module, hence they are involved in some similar functionalities. And second observation we observe is that those two key networks in this driving this connectivity trait, when you're looking at the nodes in those systems, they are prominently represented in the latent space. So the latent space can tell us which of those, what node networks is the driving, node network for each of the connectivity traits. And also, as you can see, auditory and sensory motor, they're highly connected in this trait. So not surprisingly, we can see the two group of nodes have very similar angles between them. And here is a locus representation for static FC. So very similar type of structures. The main difference here, because in static FC, each subject only contribute one FC matrix in the data input. So therefore, after we extract the latent connectivity traits, the subject's trait loading basically reduces to a single scalar variable. And those subject trait loadings, the advantage to have them is that you can readily take them to do some association analysis with subject group membership and also with some clinical symptoms. And in this way, it can help us identify which of the connectivity traits is significantly associated with clinical or behavior or population demographic phenotypes. So here's a summary of some of the nice things we locus can deliver, first of all, there is a significant reduction in the number of parameters from second order of parameters in terms of nodes to linear order. And it also offers some appealing neuroscience interpretation. One of the advantages I haven't mentioned is that using these latent coordinates of the nodes, we can define this node contribution index, which can help us to basically identify those key nodes that plays important roles in driving each of the connectivity trait. Okay. So this is useful because a lot of times in brain connectivity analysis, researchers are not only interested to identify those highly significant edges, they also wonder what are the highly important nodes. So this node contribution index can help to serve that purpose. As we have mentioned, the trait loadings are very useful output from this algorithm. For static FC, the trait loading is a scalar variable, which represents the prominence or presence of a connectivity trait in the subject. For dynamic FC, the trait loading, each of the subject, we have a time series vector of trait loading, which captures the dynamic expression profile of each of the trait. And those trait loadings can be readily associated with subjects' covariates in the brain behavior modeling. So the next thing we want to mention is the regularizations in the locus. To provide a robust estimate, basically we need to incorporate proper regularizations so the results from the algorithm will have some the desirable properties that we mentioned. Our first type of regularization is the spatial sparsity regularization, which means we want those reconstructed connectivity trait matrix to be, to have parsimonious representation. We don't want something that is overly dense with, with signals across all over the brain connectome. Okay, so to achieve that, we have the built-in this spatial sparsity regularization. We first tried some of the existing sparse messaging methods in the tensor literature. So for example, one of the most popular used ones is try to achieve vector-wise sparsity in the latent coordinates here. However, when we're looking at our endpoint of interest, is actually this connectivity matrix. Okay, so that means what we want to achieve sparsity for is this connection matrix, which are based on the inner product between pairs of those latent coordinate vectors. So using this existing sparsity regularization, it will not give us what we want, but rather introduce some structure noise, which was what we found. So for that purpose, we have developed this new inner product based or angle based sparsity so that we can obtain element-wise sparsity in the reconstructed connectivity matrices. And for temporal, in a temporal domain, when we study decomposed dynamic functional connectivity, is that we want put in a temporal smoothness regularization in the sense that we want those temporal loading coefficient to be similar with each other at adjacent time point. This is derived from the observation of the temporal similarity in the DFC matrices itself across adjacent time. So this is usually caused because the brain doesn't change that dramatically at at very close time intervals, and also because of some overlapping underlying data that is used in deriving those DFC matrices. And so this is the objective function then by building in those regularizations. The first part of the objective function is a reconstruction error. So we want to minimize the reconstruction error between the observed connectivity matrix and our reconstructed connectivity matrix based on our locus model. And then the second thing we have, then next we have the regularizations. The first is what we call the angle-based sparsity regularization, which help us to achieve element-wise sparsity in the connectivity traits. So it's angle-based because, as you can see, this element is based on the inner product between the latent coordinates of the nodes, which means that is the angle between the node pairs. And then we have the temporal smoothness regularization to have some kind of similarity in the temporal loadings at adjacent time point. So now we have the objective function. The next question is, well, how do we, learn it or optimize it? So unfortunately, this objective function is non-convex, but we have found that it has a very nice property as known as a block multi-convexity, which means is that even though it is not overall convex, but you can decompose, you can partition your parameters into some groups of parameters, and then when you optimize one group of parameter while conditional on the rest of the parameter, that optimization is conditionally convexed so that we can iteratively optimize each block of parameters in a convexity optimization manner. And so therefore we developed this highly efficient algorithm that have analytical solution at each of the step, which means we can avoid with some of the iteration that's needed in some of the other penalization method. So I will not go into too much details of this. And secondly, this is some other technical details. We actually explored some of the ICA pre-processing tricks, so which can help us to further reduce the dimension of the parameter estimations and also stabilize and facilitate our optimization. So our final optimization function actually is based on this pre-processed, whitened signal. Okay. So I'll not get too much of detail that, and this is the block multi-convexity. And this is the algorithm that we developed. Basically, we call it a node rotation algorithm. So we decompose, basically we partitioned our parameters into those blocks of parameters. For example, the mixing coefficient is A, and then the X is what the latent coordinate of those nodes are. So what we do here is that at each step, we will update the latent coordinates of one of the nodes while conditioned on the latent coordinates of all the other nodes and other parameters. And then we will rotate across all the nodes in the atlas. And then next, we're going to update other parameters in the system, such as the mixing coefficient. And then we will iterate this optimization. Basically, each of those steps have explicit solutions. And then we'll just iterate those steps until everything converges. So here is some toy example to show how this algorithm worked. This is our through simulation data, and this is the true connectivity source matrix we put in there, which we want to recover. And these are our initial estimate or guess for those connectivity matrix. As you can see, it's pretty noisy. You can see some of those patterns, of this true signal matrix, but it's kind of masked by, a lot of noisy noise around across the whole network. And when we're looking at the latent space representation of the initial latent coordinates, basically they are scattered around across all the nodes. You cannot tell much of a pattern here. And then across the iterations of Local's algorithm, those latent coordinates become more and more clustered in terms of the directionality. You can see now they become focused on two directions, major directions. And then the resulting reconstructed connectivity sources become closely and closely goes towards the true sources. And also they become sparser as well. Okay. So in this algorithm, there's something we do need technical things we need to be careful about and pay attention to, like in every low rank factorization, the key question is, one of the important questions you need to address is that, well, how do you determine the rank? What is the rank of the latent space you project those nodes to? Okay, so there are some existing methods, but they're not very appropriate for our current model. And further, for our model, because we are blind source separation model, there's another layer of challenge because we have specified a component-specific rank parameter because every connectivity trace may have a different topological structures. So we want to have the flexibility to have the component-specific rank parameter so that we can capture the features from different traits. But that basically increases the challenges in selecting those rank parameters. For example, if you extract 30 components from the data, that means you need to find how to specify 30 rank parameters. To solve this challenge, we propose this adaptive selection method. So the idea here, we'll consider the latent connectivity matrix that is estimated without the low rank structure. And then we'll consider the one that is estimated with the structure. Basically, what we will how we'll choose the rank parameter is that we will look at the difference between the unconstrained estimate versus the low rank structure constrained estimate. And then we are going to set some closeness criteria. Say, for example, we want the low rank one to be 90% close to the unconstrained estimate. So that is controlled by this proportion parameter that controlling the desired level of closeness. So once we select this desired level of closeness proportion, then this method will help us automatically and adaptively select the rank for each of the latent component so that it can achieve the desired closeness. Okay. And then there's several other tuning parameters like the sparsity for the tuning parameter for the two sparsity, regularization terms. For that, we propose to use a BIC type of criteria or using the reconstruction arrow as objective function to select them. Okay. So furthermore, as we have mentioned, one of our main goals to develop this method is to increase the reliability in the extracted latent connectivity traits. So how to evaluate such reliability? Basically, we have proposed this reliability index for blind source separation method. So this is a chance-corrected reproducibility index. What it does is that for each of the estimated latent sources, we are gonna do a lot of replication rounds on the data. And then, so basically, for example, you can bootstrap your observed data and estimate extract connectivity sources in each of the bootstrap samples. Then we're going to study how reliable or reproducible each of the latent sources are across those bootstrap samples. So we are comparing the original, we are evaluating the closeness of the original extracted sources and its matching component in each of the bootstrap, for example, replication samples. So that is basically, this is what we call the observed reliability. But this index also do some chance correction because when you take two connectivity matrix, you're always going to find some correlation or similarity between them. So that is what we call by chance reproducibility. So we don't want to include that by chance, reliability into our measure. So therefore, we would remove that by chance reproducibility and see how much our observed reproducibility exceeds what we expected by chance. So this is like a benchmark, basically, type of idea. Furthermore, we would standardize this reliability index so that it are standardized into this scale between 0 and 1, where higher reliability index will show better reproducibility. And there's also a very nice interpretation guideline in terms of how we can interpret the level of reliability based on this index value. Okay. So here we have some simulation studies, which I'm gonna very quickly show. Basically, we generated some brain connectome data using connectivity traits that are designed to mimic real connectivity traits from the data. So here we have included about 8 of them. And then we used the different methods to reconstruct those connectivity matrix. And so to show what is the performance of the various methods. So here we have shown using the proposed locus method, we can have a more accurate, reconstruction to uncover those true connectivity traits as compared to using existing algorithms. Okay, so finally, I'm going to talk about some of the analysis results using the Philadelphia Neurodevelopment PMC study. So basically, first, we did some static FC analysis. I just want to show this is one of the connectivity traits reconstructed using the proposed method versus using existing method. So basically, the sparsity regularization that we have included in our optimization helped to remove a lot of the spurious connections in the original results so that it can provide a more clear picture in terms of what are the key driving connections and nodes, in each of the underlying sources. So now we can be much more focused in terms of which connections that we should look at, okay? And so these are some more results coming from additional traits. Another thing I want to emphasize here is that because we have improved the estimate of the connectivity trait, the trait loading estimate coming out from locus also becomes more precise. And because of that, it increases our statistical power in detecting association and differences in those connectivity traits. For example, in this connectivity trait, trait 3, which is a cerebellum-driven connectivity, we did association analysis of this trait with age in neurodevelopmental in a PMC study, and the locus-derived trait loadings shows a significant age effect in this trait, which is consistent with findings of how the cerebellum-driven connection develops in this age group in the literature. Well, if we use existing method, because this is very noisy, connectivity trait map, therefore the corresponding trait loadings is not precise enough, and we cannot detect the association with age in this case. Okay, so this is some reproducibility analysis results. This shows how reproducible the results are in terms of with respect to different initialization, and this is comparing the reproducibility between locus method and existing method. So the extracted components using locus method is consistently higher than using the existing ones. And furthermore, we also have applied the method to another major neurodevelopment study, ABCD study, and we found some of the connectivity traits that we identified in PNC studies can also be found in ABCD studies. So this is something very interesting and exciting finding. So that we can reproduce these traits, across studies. So this really showed some early evidence that there are some consistent connectivity patterns, connectivity traits really underlying the functional connectome. Next, I'm going to talk about the dynamic FC analysis. And so using still the PMC data, okay, similarly, the same data sets, and we are using resting state FMI data, and we derived the DFC measures using basically a sliding window approach with a taper window structure, and this is following the papers from Vince's group. And then basically we choose a number of 30 latent components based on the reliability of the extracted components. And so basically we have looking at the 30 components, almost all of them have at least moderate reproducibility, and 18 out of 30 of them have a substantial or almost perfect reproducibility, which means the reliability index is greater than 0.6, And here I have shown 3 most reproducible connectivity traits. And very interestingly, this trait, the most highly reproducible connectivity traits in dynamic connectivity analysis, a lot of them involves connections with the visual network. So that is something that we found very interesting. And those trait loadings from the dynamic locus, as I mentioned, represent dynamic temporal profiles, okay, of each of the trait. So we can do a lot of interesting analysis using those trait loading time series. For example, we have defined the 2 measure of characteristics of those trait loadings. One is called energy. So this is sum square of the trait loadings across time. This reflects the overall energy of a connectivity trait in the dynamic connectome. Or on the other hand, it shows overall how prominent or how present this connectivity trait is across time. A second index we look at is the variation. So basically, we're looking at how much variation this connectivity trait is expressed at the adjacent time point, how much it changes from one time to the next time point. So one of the difference from previous measure of variation is that we standardize this variation by the level of energy of this trait, so that these 2 measures, energy and variation, are more independent from each other. So this variation is what we call relative variation. Okay, so here basically we can put each of the plot. Here we plot the variation versus logarithm of energy of all the 30 connectivity traits that we have extracted. And from this, you can identify some interesting trait coming out, in terms of the temporal profiles. For example, like the trait 27 has a high energy and high variation, which is this plot. Basically, what this one shows is that this trait basically has some very high prominent presence at certain time period, but then at other times during the, they kind of like goes offline. And then when we're looking at some other trait, like trait 14, it has a high energy, very high energy, but its variation is much lower than other highly expressed, trait. So which means this basically this trait is highly present and also is very consistently present across time. Okay, so we have looked at those, plotted those trait according to the energy and variation. So the high energy, high variation one that I've just shown, this is basically a long distance connection trait, which connecting the sensory motor with default mode network and also some bottom of the brain regions. Well, the high energy and the medium variation one I have shown, which is very highly present and also very consistent across time, is an executive control trait, which I'm going to coming back to. So, and then the one interesting one we also found is very low energy, also very low variation. So this is a cerebellum driven trait, which is mainly driven by the connection between cerebellum and the rest of the brain. So the analysis from its temporal profile indicate this is a very stable background connectivity trait, which means it's present there almost all the time in a dynamic connectome, but it's a low energy, which is kind of like a kind of background type of connectivity pattern in a whole connectome. Okay, so we can also investigate the interaction and synchronization between the trait by using the cross correlation between the trait loadings of pairs of nodes. So what I want to mention here, we have displayed some of the highly synchronized or associated connectivity trait pairs. One of the things we notice interesting coming out of it is that the trait 14, which is this highly consistent, highly expressed executive control trait, it also shows up a lot in this synchronization analysis, which means this trait is actively being cooperating with many other connectivity traits, basically. Okay. So furthermore, the trait loadings from locus offers a convenient way for us to do, association analysis. Here we take the trait 14, executive control function trait, which is driven by the connection involving the EC network. And then we modeled the logarithm energy of this trait in terms of age and gender of the subjects. And what we found out is when children grows up, the energy or the presence of this trait increases in both genders. However, the trajectory of development is different. For female, which is the red boxes, this trait develops earlier from childhood to adolescence, and then it gets stabilized. For male, in this early time period, this trait doesn't change much, but then there's a very dramatic increase from adolescence to early adulthood. So which suggests that this connectivity trait actually matures later in male as comparing to female. Furthermore, when you're looking at the adulthood, during adulthood, the presence of this trait is much more prominent in male individuals as comparing to female. So this shows some very interesting insights about this executive trait. And finally, sorry, I'm trying to quick and summarize. And as we have mentioned, in dynamic connectivity analysis, one of the common goals is to identify those whole brain DFC latent states. Using dynamic locus, we actually can come up with a very efficient pipeline to do that. Basically, what you do is that you take the dynamic connectivity matrix and you run it through Dynalocus. Then it will project those matrices into those latent connectivity matrices, extract those latent connectivity matrix, and then it also produces the subject's trait loading time series across each of the subjects. So those trait loading series actually can be viewed as a low dimensional re-representation of those original DFC matrix after we project those matrices onto our connectivity traits matrix set. So this set of connectivity trait matrices can be viewed as a basis set of matrices. And then this becomes the low dimensional coordinates after you project the original DFC matrix onto this basis set. Then for the next step, instead of clustering the original DFC matrix, which is high dimensional, we can clustering, those trait loading series to identify the clusters of trait loadings. And then once we identify those centroids of the clusters, after clustering those trait loadings, then we can multiply them with the connectivity trait matrix basis to basically reconstruct the latent DFC states. Okay, so this is kind of like you first shrink your original DFC matrix into this low dimensional space, and then you do the clustering in the low dimensional space, which is very fast. And then later you inflate them back again onto the original connectivity matrix space. So use that, we have identified 7 latent DFC states using the PMC data. And a very interesting finding from this this method is that not only can we identify those latent connectivity, DFC states, now we can also identify which of the latent connectivity traits is driving, those latent state. For example, for this most dominant latent state, which is present like 34% of the time, we can see the key driving connectivity trait is trait 14. So again, this is that executive control trait and some other trait, basically. And also to validate our findings, we analyze the same data using that very highly cited Allen's method paper, that DFC paper by Vince group. So basically, this is one of the most highly cited dynamic FC papers. So we used this method on the same data. And very interestingly, the two methods have a different way to identify the total number of latent states, but both of them identified 7 latent states from the data. And also, we can very well match our extracted latent state with the, the latent state kind of recovered by Allen's method. You can see basically the patterns in our latent state. You can find the corresponding patterns in the Allen's method's estimate. Furthermore, we find the presence proportion also is very, very close between the two methods. So this really boosts our confidence that the latent states identified by Dana locus using that our new pipeline actually is finding something that is neurologically meaningful. And we are very, very happy to see actually there are such closeness and corresponding, finding using these two different methods. So this kind of further validate really, interestingly, there seems to be 7 latent states underlying this data. Okay, so again, I think I'm over time, but these are just some summaries. And basically the key idea is that we're using neurobiologically motivated low-rank tensor factorization to improve the reliability in recovering those latent connectome traits. And those trait loadings offers some very interesting approaches to do whole brain DFC latent states estimation, and also offer some new insights into the temporal expression profiles. And finally, we have prepared the packages for these 2 methods. They are available at our website. And here, acknowledgement, this is Jialu, Yikai, and Yao Tian who have contributed to this work, and the research support is from NIH and Emory. Thank you, that's all.
Thanks very much. That was great. So I don't know if I have some questions, but I don't want to ask my questions. I'd like to see, at least initially, see if others have questions first.
Yeah.
Armin, do you see any?
I don't see
Please feel free to post in the chat or just unmute or let us know and we can unmute you. One question I had was, I thought it was really interesting, but one thing we think about here a lot is how, and Armin's done a lot of work in this too, is the concept of like a functional unit, where if you're doing clustering or ICA or something like that, you're letting the data tell you where the groupings should be, right? As opposed to using an atlas from external. So obviously you have to pick where you start, right, in all of this stuff. But I was just curious whether you have any thought of maybe I think you were using the Power Atlas, I think, in this, and so whether you were thinking of kind of moving to maybe you could do ICA, you know, using either one of your approaches or one of ours or somebody else's before and feeding it in, right, to Locus or integrating them together, right? So I just wanted to get your thoughts on that. Yeah.
So are you talking about like integrated pipeline where you start from the, for example, FMI both signals, and then you will identify those functional units and then subsequently extract.
Right. Yeah, because I think the concern that with the Atlas is that you may not be grouping voxels together that should be grouped together, right? Because you're using an external sort of hard parcellation that's fixed based on whatever the Atlas used. So yeah, just curious. I mean, I know you think about this too, so I'm just curious what your thoughts were on that.
That's a very good question. That's a very good question, Vince. Yeah, definitely, because as you mentioned, both of our group have done a lot in terms of using ICA to decompose FMI time series to identify those functional units, right? Which may vary from study to study and from population to population. So yes, the answer is yes. We can potentially use in the function, you know, those ICA or other source separation methods on the you know, neural activity data first to identify the most relevant functional units in the data sets, and then construct the connectivity matrix based on those data-dependent functional units. And then from that, Locus methods can be used to decompose that data-driven, you know, unit system-based connectivity matrix. Yes, yes. And I think that may probably yield even more. I would suspect it will yield some even more prominent patterns in the resulting connectivity traits, because your node system is already first optimized based on the observed data. So they are the most relevant functional units. Basically.
Right.
Yeah, exactly.
Yeah. I think it may help. Yeah, like you said, even further. So yeah.
Yes.
Great.
So Alireza, I have a question, and also Jean Louis. So Alireza, you can ask your question yourself.
Hi, Ian. It was a nice presentation. Thank you. Can you please go to your slide number 21?
Oh, okay. Let me share my slide again. Slide 21. Okay.
Actually, I have two questions. One of them is related.
Yeah, here's the slide 21.
Yes, actually, so when you are solving this optimization problem, right? I mean, as typical in ICA, you start with a linear like model, like these A's, right? So can you please share with us like what would happen if we consider a non-linear mapping? So how to handle non-linearities? You see what I'm asking for?
Yes, that's a very good question. I think in the ICA literature, like the original ICA model is a linear separation, basically linear combination of signals, because that is, you know, first of all, linear is kind of like the first step approximation, right? You can then, if you go to linear, basically is a first order approximation of your signal, basically. So it offers a lot of mathematical advantage to work on the linear approximation, but definitely the linear approximation may not be perfect for all scenarios. So that's why in the ICA literature, there's a nonlinear separation, you know, method as well. We call nonlinear ICA. So which means then this reconstruction function is not a linear combination function, but rather some nonlinear function, something we denote with F. I think that is doable, definitely. For future direction for Locus is that instead of considering this a linear reconstruction, we can use some nonlinear reconstruction of, you know, based on latent sources, and which can potentially provide close, you know, more close approximation to your real data. However, that will involve additional technical challenge, of course, you know, in the optimization. So one of our recent paper is called a distributional ICA, which is have some similar flavor. What we did in that one is that we'll first project the data into some distributional space, and then using the weights in that distributional space to and fit a linear type of a source separation, and then goes back to the original data. So the idea of that is that because when you are doing a linear combination or linear reconstruction in a distributional space, you can still recover non-linear mixture in your original data source domain. So that is one of the strategy that we used in our other work to help recover non-linear, reconstructed sources. Yeah, but we haven't directly worked on, non-linear reconstruction for the locus methods yet, which could be something we may, try in the future and see how much gain, the non-linear mixture can offer over the linear one. Yeah, thank you for the question.
Good. Yeah, the second question I have here is this minimization for sure is over all the a's, little a's, right? Is also this XL like U and XLV, the coordinates of that latent space also included in the variables of the optimization, or no, it is just microbiome? Okay.
Yes. Yeah. Thank you for the question. I didn't have time to talk all the details. Yes, when we estimated, let me see what I have that. I have the algorithm, right? When we estimated, basically we estimate everything. We estimate X, we estimate D, we estimate A. All of them.
So then I understand now what's happening. So now the last question I have is the following. So what I have, what is given is Y. Y sub I T, which how many of them I have? I have capital N multiplied by capital T of them, right? This is number of observations I have.
Oh, you mean Y's?
Yes, that is given. That is my observation, right?
Yes.
Then if you think about it, little a has exactly the same number of unknowns as Y multiplied by Q. I have much more number of unknowns. And now I'm adding even more unknowns through X, through L, and that's it. So essentially what I'm after here is that number of given things I have is much less than number of unknowns. And
okay. Yeah. Let me just clarify here. This is YIT, so it's a bolded vector. Basically, the dimension of YIT, each of the YIT. So the YIT basically is the observed dynamic connecting matrix at that specific time. So its dimension is this actually. So it's a number of nodes, the total of number of node pairs in the matrix.
Okay, thank you. So, it was helpful. Thank you very much.
Yeah, thank you for giving me the chance to clarify on that. Yeah. Okay.
All right.
I'm sorry.
Yeah, go ahead.
I have time.
Yeah, please.
Yeah.
Sorry, I didn't leave much time for questions.
But it's a very excellent talk, and the mixtures are very clear. I like the concept of this latent trait, right? Instead of state, there's a latent connectivity traits to say there are some unique things in this connectivity. Just much related to the question just asked regarding the linear decomposition. It's just curious to know, because I just run into a paper, have the similar concept. I can have this FNC matrix, however, I dissect into 7 or 8. They didn't use trait, but some different base FNC matrix, right? So use that as a base matrix, so like you would use that as a trait. And then linear combination of them to form my final traits. However, they build this model using deep learning. So they build in the nonlinearity in. So that's like, oh, okay, that's a very similar concept to try to get some of your thinking that the previous question already asked about this linearity and nonlinearity.
Yeah, thank you for the question. Oh, so is that, are you asking about the connection between the method, or?
Well, I'm just curious to know, because they already did this big deep learning built into the nonlinear similar idea concept, like what's your direction? You probably already answered that you want to build into nonlinear.
The answer is always just do deep learning, right? Isn't that the answer?
Well,
okay. Yeah.
I'm not sure, Vince. I'm not sure. You have to consider.
I know.
Yeah. Well, basically, that's a good question. So, my sense is that, first of all, if you build deep learning and to recover those connectivity trait matrix, if you don't, basically is that you have to think about how many parameters you need to optimize in that deep learning trait matrix. And then what is the sample size that's needed to support that? I don't know about the specific paper you're talking about. So basically, our experience with deep learning is that it really requires a large sample to produce reliable estimate. If you don't build in some constraint or some structures in your parameter space in your deep learning model. So that is actually what we are doing here exactly is that we are not going deep learning yet. It can potentially go that way. But what we are doing here is that let's find out what is a latent space structure that can best help us, to reduce the already large number of parameters we need to estimate in a regular analysis. And whether we can already achieve a very good approximation, using, once you find the appropriate load, this tensor structure, we find it can help a lot in terms of reduce the parameters in estimation and improve the robustness in terms of the estimates. And you can do this. We have tried different sample sizes also in different data sets. And the algorithm generally is what we find is pretty robust. So it's not like it will work in one data set and broke in another based on our experience. So that's something that I'm feeling comfortable with. Yeah, maybe someday we'll move into deep learning and by building the low rank structure. But I think those kind of tools will work very well in certain scenarios. But I'm not sure they are needed, and also they will work perfectly in all scenarios. Yeah.
Yeah,
It's a safe answer.
If I can add my 2 cents. So in fact, we are doing some stuff with the connectivity domain. Basically, we try to capture the nonlinearity in the connectivity domain. Then we can apply linear ICA, basically. Same concept of the kernel PCA, kernel ICA.
Yes.
But the idea is that we calculate the connectivity nonlinearity in the connectivity domain, then we can follow up. Yeah.
Yes, exactly. If you can project your data into some appropriate domain, basically it'll be linear in that domain. And then you can do a lot of very convenient estimation optimization and then go back to the nonlinear original space.
Yeah. So similarly, you can also, we've been doing a lot of work sort of initializing models using these types of approaches, which it improves performance quite a bit, right? It's sort of, so you take, you could take ICA and feed it in, right, to
very good point.
To deeper models, things like that, right?
Yeah, exactly. Yeah, exactly.
And it's too bad we lost Sergey Pliss. He has some interesting thoughts on how much data you need to train deep models, things like that. So that'll be an interesting conversation for later.
Yeah, I'll be love that. I know Sergey work a lot on, his focus is in deep learning methods. That's some of his papers. Yeah.
So I think maybe we should sign off now, but just as a reminder for BrainSpace Initiative, there's a Slack channel and the questions will be, if there's any left, will be preserved there, and we can have ongoing interactions in that channel, and there'll also be a recording available as well. So the idea is to kind of, allow a little bit of follow-up that we can't do due to the interest of time on the live call here. So thank you very much, Ying, for joining us. It was really interesting to hear about your work.